So last time around, we looked at different ways to define functions, and we saw that some were familiar, like conditional expressions, and some were new, like pattern matching. So what we're going to be doing today is looking at the idea of list comprehensions, which are a simple but powerful idea for programming with lists in languages like Haskell. And actually, this idea has now also been incorporated into many other programming languages too. So for example, it's in Python, Ruby, Scala, F#, and many more. So the starting point for this, as many things in this course, is to look back to something that the mathematicians already use. And this is the idea of set comprehensions. So it's a very simple one. So in mathematics, the comprehension notation can be used to construct new sets from old sets. So what I'm doing here in the little blue box is I'm constructing a set. So I know it's a set because I have the curly parentheses or squiggly brackets, as I like to call them. And the way that you read this is I'm building the set of all numbers x squared such that x is an element of the set 1 to 5. So I'm taking an existing or old set 1 up to 5 and I'm processing it by simply squaring each of the numbers. So I'm going to get the set 1, 4, 9, 16 and 25 coming out of this set comprehension notation. So very, very simple idea which you should all be familiar with if you've done any discrete maths before. So in Haskell, we have exactly the same idea, but for lists rather than sets. So in Haskell, a similar comprehension notation can be used to construct new lists from old lists. So here in the little blue box is the same example written in Haskell notation. We're building the list this time, and we know it's a list because we see the square brackets rather than the curly brackets. So it's the list of all values x to the power 2, so the little hat symbol is raising to the power in Haskell, and then we have the same vertical bar as in set comprehensions, which we read as such that, and then we say x is drawn from, or as an element of, the list from 1 to 5. So here we're taking the old list, 1 up to 5, which is just 1 dot dot in square brackets in Haskell. We're selecting the elements from it one at a time, and then we're squaring each of those elements. So in this case, we will get the list 1, 4, 9, 16, and 25. And at this point, you might be thinking to yourself, actually, what's the difference between a list and a set? And the basic idea is that in a set, the order in which elements appear doesn't matter, and duplicity, or how many times each element appears, doesn't matter either. So if I look back to the previous slide, and I have the set 1, 4, 9, 16, 25, the order in which I wrote things there doesn't matter, because it's a set, and how many times I wrote each of the numbers doesn't matter either. So if I had 5 copies of the 1, that would be the same set as what I've written on the slide here. All that matters with the set is whether an element is in the set or not how many times it appears or where it appears. Whereas with a list, the order in which you write things matter. So 1, 4, 9, 16, 25 is a different list than if we started permuting the elements around. And also how many times we write a number in a list matters as well. So there's a couple of points to note here, as usual. So the first point is that the expression x back arrow 1 to 5 is called a generator, as it states how to generate values for x. And the way I like to read this is x is drawn from the list 1 up to 5. And the comprehension notation allows you to have multiple generators separated by commas. And this is a very simple and a very natural idea. So here is an example of this. So I've started up GACI and I have the little greater than prompt here, and I'm forming a list using the comprehension notation. So we can look at the different components of this. We're forming the list of all pairs x, y such that, and then we have 2 generators on the right hand side. So the first generator says x is drawn from the list 1 up to 3. And then we have a second generator, separated by a comma, that says y is drawn from the list 4 up to 5. So we have 3 ways of selecting x. We have 2 ways of selecting y. So there's going to be 3 times 2, which is 6 ways of forming a pair. So what you see in the output is we have all possible pairs of a number between 1 and 3 and a number between 4 and 5. And again, there are 6 different ways of doing this. And you may look at this and actually you might think, well, I've seen something like this before, and this example is very similar to the idea of Cartesian products of sets. So if you have a set A and a set B, and you form the Cartesian product A times B, that's all the pairs comprising one element from A and one element from B. So this is kind of like the Cartesian product of the list 1, 2, 3 and the list 4, 5. So changing the order of the generators in a list comprehension changes the order of the elements in the final list. So if we take the same example and swap round the two generators, this is what we get. So we're forming the list of all pairs x and y, such that this time we have the y generator first, so y comes from the list 4 up to 5, and then the x generator comes second, so x comes from the list 1, 2, 3. And what we see in the example is we get the same pairs, but they come out in a slightly different order. And the way to understand this is very simple. So multiple generators are like nested loops, with later generators as more deeply nested loops whose variable changes value more frequently. So we can think about this example a bit operationally. We can think of it as being a bit like a for loop, or a nested for loop. So if we look at the example kind of in an imperative way, this would be like saying for y ranges from 4 up to 5, and then as an inner loop we have for x ranges from 1 to 3, and then we're returning the pair x, y. So this is showing us that the x component is going to change quickly because it corresponds to the inner loop, and the y component is going to change slowly because it corresponds to the outer loop. So if we just wanted to bring this point home, we could have a little picture to illustrate it. If we look at the output here, we see because x is the last generator, x is coming from 1 to 3, the x component is changing fast. So if we look at the pairs, we have 1, 4, 2, 4, and 3, 4. So the x component, the first component, is changing fast. Then once the x loop has run once, y will click over to 5, and then x will go from 1 to 3 again. So we get 1, 5, 2, 5, and 3, 5. So again, just to emphasize the point, x drawn from 1 to 3 is the last generator, so the value of the x component of each pair changes most frequently. So this brings us on now to the idea of what's called dependent generators. And this is a very simple idea, and the idea is that later generators can depend on the values that are introduced by earlier generators. So here's a little example of this. It's a bit of a contrived example, but it illustrates the point. So we're building the list of all pairs x, y, such that x is drawn from the list 1 to 3, and y is drawn from the list x to 3. So we have two generators here. X is the outer one, and y is the inner one, and the value of y now depends on the value of x. So we can work out what is the output for this going to be. So initially x will be 1, and then y will range from 1 up to 3. So we'll get the pair 1, 1, 1, 2, and 1, 3. And then x will click over to 2, and then y will go from 2 to 3. So we get 2, 2, and 2, 3. And then x finally goes to 3, and y ranges from 3 to 3. So we finally get the pair 3, 3. So what we see in the callout box, we get this list, and it's the pair, all pairs of numbers x, y, such that x, y are drawn from the list 1 to 3, and y is greater than or equal to x. So it's a bit of a contrived example. Let's have a much more natural and compelling example, and it's given by the concat function from the standard library. So this is not a function we've seen before, but it's a very simple and a very useful one. So we can see what it does down at the bottom of the slide. Concat takes a list of lists, in this case a list of numbers, and we have one inner list, 1, 2, 3, we have a second one, 4 and 5, and we have a third one, 6, and it just smashes them all together, and we get one simple long list, 1 up to 6. Okay, so it just takes a list of lists and smashes them all together to give a long list. Let's look at the definition now. So the type is straightforward. It's a function because we've got the arrow. Its input is a list of things of type A, and its output is a single list of type A. So it's a polymorphic function because we have a variable there in the type. And then what the definition says is it's a nice one-liner with a list comprehension. We have simply two generators. So we're saying concat of a list of list with two s's on it, x's. So remember, we use this convention. If a parameter to a function is a list, we put an s on it. So if it's a list of lists, we put two s's. And then if we look to the right-hand side, what are we doing? We've got an outer generator. which is ranging over each of the component lists. So it will take each list x's one at a time. And then we've got an inner generator, which is ranging over each of the values in those component lists. So again, if you wanted to think more operationally about this, it's like a for loop in an imperative language. It's kind of saying for each list x's in the outer list or the main list, x's with two s's, then we're going to have an inner loop, and that's for each x in each of those component list x's, and then we're going to return the value x. Okay, so it's a nested looping structure which is running over each of these lists in turn, and then each of those values in those lists, and we get the desired behavior. So the only other thing you need to know about list comprehensions is guards. So we have two things in list comprehensions. We have generators which produce values, and we have guards which throw them away. So list comprehensions can use guards to restrict the values produced by earlier generators. So here's a really simple example of this. We're forming the list of all values x such that x comes from the list 1 to 10. So that's a generator. And then we have a comma. And then we have the guard even of n. So even is a library function that simply takes an integer as a parameter and returns true if it's even and false if it's not. Okay, so what we're going to get back this time is we're going to get back the list 2, 4, 6, 8, 10 of all the numbers x, such that x is the element of the list 1 to 10 and x is even. So the guard is kind of filtering out or removing elements which are not even. And again, if you want to think more operationally or imperative about this example, it's really like a for loop. So you've got for x ranging from 1 to 10, and then inside the loop you're saying if x is even, then we return it, otherwise we throw it away. Okay, so this is basically now all you need to know about list comprehensions. You have generators and you have guards, and that's it. So let's have a more interesting example now of using list comprehensions. And what we're going to do is write a little program that generates prime numbers. And the first thing we're going to do is define a little helper function for this. So what we've got at the bottom of the slide is an example. We've got a function called factors, and it takes a number like 15, and it's going to tell you the numbers which divide into it precisely. So these are the factors or the divisors. So in the case of 15, there's 4 factors, 1, 3, 5, and 15, which we're going to return in a list. And then at the top of the slide, we see how the factors function is actually defined. We say factors is a function that takes an integer as its input, and it gives a list of integers as its output. It's just a simple type here. And the definition is a one-liner. We have one generator and one guard. So factors of n is going to be the list of all numbers x such that x is drawn from the list 1 to n, and when we divide n by x, the remainder had better be 0. So what the mod function does here is it divides one number by another number, and it gives you the remainder, and we're checking if the remainder is actually 0. So whereas we've seen div, which is the integer division operator, which we often write as an infix operator using the backquote syntax, mod is the integer remainder operator, and we give back, we're checking if the remainder is 0 in this case. So a quick reminder again, equality in Haskell is double equals. Single equal is used for defining functions. So when we want to check if the remainder is 0, we must write a double equal sign. So nice simple one-line definition using a list comprehension. Then we can move on to defining a function that tests if a number is prime. So a positive integer is called prime if its only factors are 1 and the number itself. So let's look at the examples first as usual. So 15 is not a prime number, so we want to return false here. And it's not prime because it's got too many factors. The factors of 15 are 1, 3, 5, and 15. So it's not a prime number. Whereas 7 is a prime number because its only factors are 1 and 7. So 1 and the number itself, so this is a prime number. So we can use this idea to write a simple one-liner at the top of the slide. So prime is a function. It takes an integer as an input, and it gives a boolean back as an output. And all we're going to do is simply call the factors function with the parameter n, and that's going to give us a list. And then we're going to check, again, using the Haskell double equals for equality, whether the list that comes out of that is exactly 1 and n, and nothing else. Okay, so this function will have this behavior here. And you might be thinking, well, this looks horrendously inefficient. It looks like if I want to calculate the factors of a million, or calculate whether a million is a prime number rather, I first need to calculate all the factors of a million, which may take quite a long time, and then check, is it equal to the list 1 with a million in the end, just those two numbers. But actually, under lazy evaluation, that equality check, as soon as it finds something which is not either 1 or the number itself, that equality check will stop and give back the result false. So this function is actually much more efficient than you might think it is because of lazy evaluation, which is the mechanism that Haskell uses to execute your programs. And again, we'll see more about lazy evaluation later on in the course. So the last thing I want to do here is wrap up the primality example by showing you how you can define a function now that returns all primes up to a given limit. So down at the bottom, if I want all the primes up to 40, what I want is that list of 10 or 11 prime numbers down the bottom. So I can define this now using a very simple program. It's a list comprehension. So primes of n is going to be the list of all values x, such that x comes from 2 up to n with one generator, and then we're just going to have one guard which checks is the number actually prime. So you can type this program in for yourself, which is fun to do because it's just a very simple few lines to actually start printing out prime numbers. And you can try it for yourself. You can say, oh, if I print the first 10,000 primes, how long does that take? And you'll find it takes a little bit longer than you might think. What we will see later on in the course is a much, much faster program to generate prime numbers. But what I'd like to do actually now is just swap to using GHCI and give you an example of this prime number program running in practice and the faster one which we're going to develop later also running in practice. So what I've done now is typed these three functions in to do with prime numbers. So we have the factors function, we have the prime function, and we have the primes function. And I've loaded them into GHCI. So what I can do now is test to see is this thing actually working okay and how fast is it. So for example, I could say, what are the prime numbers up to 15,000? And it's going to slowly print out all of these, and it takes about 5 or 6 seconds to print these out. And this is quite a nice machine here. This should be a lot faster than this, but in fact we can make it a lot faster by using a better algorithm. So there's the algorithm which we've been thinking about, which is a simple primality checker. Here is a much faster algorithm, which is called the sieve of Eratosthenes. And we'll be learning about this later on in the course when we look at lazy evaluation in more detail, because this program relies very heavily on lazy evaluation. And in fact, it's doing something which kind of sounds impossible, but is quite fine in a lazy language like Haskell. It's actually building the list of all possible prime numbers, which is actually going to be an infinite list. And it's doing this by sieving an infinite list. We're starting with a list 2 up to infinity, so this is already a weird idea here. This is an infinite list beginning with 2. We're passing it into a function called sieve, and then it's going to compute all possible prime numbers for us. So we'll see how this program works later on in the course when we look at lazy evaluation in more detail. But for now, just let me show you this program working as well. And what I'm going to do is I'm going to write take while less than or equal to 15,000 and then all primes. And you might think, well, what does take while do? Well, take while is a library function, and you give it a property like being less than or equal to 15,000, and you give it a list, and it's going to keep consuming values from that list until the property is no longer true. So what this is going to do is take the infinite list of all prime numbers, and it's only going to print out those which are less than or equal to 15,000, and then it's going to stop. And what we find when we hit return here is that this program is much more efficient than the previous one. The previous one, which we wrote, took about 6 or 7 seconds to print out the numbers. This one was more or less instant. And if we wanted to, we could actually just run this and print out all the prime numbers, which is an infinite list. And this will just keep printing out these numbers forever. So back to the slides now. What we're going to do is spend a few moments thinking about the zip function, which turns out to be very useful when you're programming with list comprehensions. We've seen zip a couple of times before, and you can basically understand what it's doing just by looking at its type, first of all. So what zip does is it takes a list of A things, and then it takes a list of B things, and it gives you back a list of pairs of A and B things. And in particular, what it's actually doing is just pairing up the corresponding elements from the two lists. So again, let's have a simple example of this. If we zip the list of characters, A, B, C, with the list of numbers 1, 2, 3, 4, we pair the A with the 1, we pair the B with the 2, and we pair the C with the 3. And then the second list is now exhausted. There's nothing to pair with 4, so we just truncate and we get back these 3 pairs here. Okay, so zip takes a list of one thing, a list of potentially different things, and just pairs up the corresponding elements. So let's think what we could do with zip, and we're not quite at the point now of doing a list comprehension, but this is going to be a little helper function which is going to let us do something interesting in an interesting way. So what we can do with zip here is we can define a function that returns the list of all pairs of adjacent elements from a list. So what does this mean? Let's look at the example at the bottom. Here I'm applying the pairs function to the list 1, 2, 3, 4. And it's going to give me back the pairs of adjacent elements. I'm going to get the 1, 2, and the 2, 3, and the 3, 4. And you think, well, how could I define this? Well, actually, you can define it in a very elegant one-liner using zip. So what pairs is going to do is take a list of A's, it's a polymorphic function, and it's going to give you back a list of pairs of A's. So that's the type. And then the definition simply says, if we want the pairs from a list X's, all we're going to do is zip X's with its tail. So what's going on there? Well, it's very simple. If we look at the example, X's would be the list 1, 2, 3, 4. And then we take its tail, so that removes the 1, so we get 2, 3, 4. So if we zip 1, 2, 3, 4 with 2, 3, 4, we get exactly the list which you see in the example at the bottom. Again, this is illustrating the idea that in Haskell you tend to think in a very different way than you would think in most programming languages. This is not typically how you would do it in a more traditional language. So what can we do with pairs now? Well, we can use pairs to define a very elegant one-line function that decides if a list of things are sorted. So let's look at the two examples at the bottom. So 1, 2, 3, 4 is sorted, and 1, 3, 2, 4 is not sorted. And you think then, well, what does it mean for these one list to be sorted and one list not to be sorted? Well, it means that all adjacent pairs are in the correct order. So if we look at the first list, 1, 2, 3, 4, 1 and 2 are in the correct order, 2 and 3 are in the correct order, and 3 and 4 are in the correct order. And this is not the case in the second example, because if we look in the middle here, 3 and 2 are in the wrong place. So in order for a list to be sorted, all adjacent pairs must be in order. And using the pairs function then, we can define a nice, simple one-line definition for this. So again, as usual, let's look at the type first of all. So sorted is taking a list of things of type A and returning true or false, depending on whether it's sorted. But notice here we need a little class constraint that the type A supports an ordering, because of course, to check if if one list is sorted, we need to check whether particular elements are actually in the right order. So we need the less than and the less than or equal to operators to be defined. So that's what the type means. What does the definition mean? Well, we can kind of read this one backwards. Let's start at the end. What we're going to do is, given a list X's, like 1, 2, 3, 4, in order to decide if it's sorted, we first of all call pairs. So this will give us the pairs 1, 2, 2, 3, and 2, 4, and 3, 4. And then for each of these pairs, we're just going to check in the list comprehension, is the X component less than or equal to the Y component? So we'll check, is 1 less than 2 in the first example? True, so we'll get yes for that. Is 2 less than 3? That's correct as well. Is 3 less than 4? That's correct as well. So in the first example here, 1, 2, 3, 4, we would get the list true, 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 because the pairs of adjacent elements are all in the correct order. And then all we want to do is AND together that list of Boolean values, and AND will only give back true if everything in a list of Boolean or logical values is true. So this is a nice one-line definition which checks if a list is sorted. And it's basically using the definition of what sorted means. A list is sorted if all the adjacent pairs are in order. So again, nice simple example of a list comprehension. So let's have another example of doing something a bit more interesting. So here we're defining a function called positions, or which returns the positions of a value in a list. And we're going to use zip to do this. So if we look at the example down the bottom, if we want to find the places where 0 appears in this list of ones and zeros, then what we would do is we kind of run along that list and we'd see the places where the 0 appears. So the 0 appears in position 1, position 2, position 4, and position 7. And remember, in languages like Haskell or basically in any programming language, when you're indexing into things or looking at the positions of things, you typically count from 0. Okay, so we get 1, 2, 4, and 7 as the positions here. So how does this definition actually work? So the type, first of all, says it's a curried function. We take a single thing of type A, then we take a list of things of type A, and we're going to give back a list of integer positions or integer indices. And again, we need a simple class constraint on here because we're going to check are things actually equal. So just going back to the hints and tips I gave you about types, if you typed in this definition yourself and you weren't sure of the type, you could just ask Haskell to calculate it for you. You could type it in and say :type positions, and it would give you hopefully exactly that type here. So now let's think, how does the definition actually work? So we're taking a value x, so that's like our 0. We're taking our list x's, so that's like our list of binary digits, ones and zeros down the bottom. And then what we're doing inside the list comprehension is we've got one generator and we've got one guard. So what the list comprehension is doing is it's using zip to pair up each element with its position. Okay, so we're zipping the input list x's with all the positions from 0 onwards. And notice here that 0 onwards is actually an infinite list, or actually a potentially infinite list, and we're actually relying on lazy evaluation here to truncate things for us when the zip runs out of the first argument. And again, we'll start thinking more and more about infinite lists and lazy evaluation as the course goes on. So the zip is going to pair each element with its position, and then we'll consider each of those pairs x prime. So x prime is an element of the list, and then I is going to be the position at which it appears. And then we can move over to think about the guard. So the guard says we're only going to consider each of these pairs if the value x actually is equal to the value x prime, because that's what we're looking for. We're looking for the value x. And then for those, we're only going to keep the indices. So that's why we have the I on the right, on the left-hand side. So just to recap here, given a value x, given a list of things x's, what we're going to do is calculate the list of all indices I such that the pair x prime comma I is from the zip of the list with all the indices, and we only want to keep those pairs where x equals x prime. Okay, so a little bit more of a tricky Haskell program here. This is one of these things where you might want to kind of pause the video for yourself and think, how does this actually work? Put the slide away and think, could I rewrite this for myself? And make sure you can do these kind of things. So the basic message here is that zip is a very useful function when you're programming with list comprehensions. So the last thing I want to do today, before we move on to some examples as usual, is look at the idea of string comprehensions. And this is a really simple idea. A string is just a sequence of characters enclosed in double quotes, but internally to Haskell, strings are actually lists of characters. So if I write a string in double quotes like ABC, that is a string, but internally, and this is how it's actually implemented, the string is simply the list of individual characters A, B, and C, and that's a list of char. And you can guess what's coming next. Because strings are just special kinds of lists, they're lists of characters, any polymorphic function that operates on lists can also be applied to strings. So for example, I could take the length of a string and get 5. I could take the first 3 things off a string, A, B, C, D, E, and get ABC, and I could apply polymorphic functions like zip to strings as well. Okay, because the zip function works with any kind of list, and a string is a special kind of list. So no problem with that. So similarly, List comprehensions can also be used to define functions on strings, because strings are just lists of characters, so we can process strings using list comprehensions. So here's a simple example of this. What I'm doing is I'm defining a little function called count, and the example says if I want to count the number of times the letter S appears in Mississippi, which people always spell wrong, I did have to look it up, there's 4 S's in Mississippi. So how could I write a little Haskell program which does this? Well, I can do it using a list comprehension because I'm processing a string here, which is just a list of characters. So all I'm going to do is I'm defining the function called count. It takes a character as input and then a string as an input. So it's a curried function with 2 parameters, one at a time. And then it's going to give you back an integer, which tells you how many times does that character appear in the string. And the way we're doing this here is, again, very different from the way you'd think about it in a traditional programming language. So the definition says if I'm trying to count the number of times the character X appears in the string X's, here's what I'm going to do. So I've got a list comprehension, and I'm going to take each character X prime from the list, and then I've got a guard which says I'm only going to keep the character if it equals the one that I'm looking for. So that little list comprehension, for our example at the bottom, that would return the list comprising the 4 S's which are in Mississippi. And then we take that list of 4 S's and we simply compute its length. Okay, so a very nice Haskell style way of defining this count function. If you were doing this in a traditional imperative language, you'd probably do it using a variable. You'd set some counter to 0, and then you'd walk over the list, and every time you see the character, you'd increment the counter by 1. That's not the kind of thing you do in Haskell. You tend to process entire data structures. So we're taking the data structure, which is the list, Mississippi, we're filtering out the 4 S's, so that gives us a new data structure with 4 S's, and then we compute the length of that. And again, you don't worry about efficiency, you let the compiler make your programs efficient for you, which it's very good at doing. So again, it's the 3 C's, remember. You write clear, concise, correct programs, and you let the compiler worry about making them efficient, which again, it's very good at doing. So let's move over to the exercises for today now. So I've got 3 exercises for you. So the first one is to do with right-angled triangles, and we're going to be looking at Pythagorean triples. So a triple XYZ of positive integers is called Pythagorean if those are components of a right-angled triangle. So x squared plus y squared equals z squared. So what you've got to do is, using a list comprehension, define a function that returns Pythagorean triples whose components are in a given range. So for example, down at the bottom, if we give Pyth the number 5, it should return all the triples, x squared plus y squared plus z squared, where all the numbers are in the range 1 to 5. So you can think, how do you define this? The second example is to do with what's called perfect numbers. So a positive integer is called perfect if it equals the sum of all of its factors, excluding the number itself. So for example, down the bottom, 6 is a perfect number because if we think, what are the factors of 6? We have 1, 2, 3, and 6. So if we get rid of the 6, we exclude the number itself, and then we add up the other factors. So we add up the 1, 2, and 3, then we get the original number. So 6 is a perfect number, turns out 28 is a perfect number, and 496 is a perfect number as well. So what you've got to do here is, using a list comprehension, define a function that returns all the perfect numbers up to a given limit. So for example, these are all the perfect numbers which are up to 500. The last example here is a kind of mathsy one, which actually is going to illustrate something quite nice about how you can implement things in Haskell. So this is the idea of scalar product. So this is normally applied to vectors, which are basically just lists of numbers. So here we have the scalar product of 2 lists of numbers, x's and y's, is given by the sum of the products of the corresponding integers. So we have this big summation here. I is the indices into the list, ranging from 0 up to n-1, and we're going to take the ith component of the first list and multiply it by the ith component of the second list. And you can think, what's a nice Haskell-y way to define this? So what I'm going to do now is swap to my iPad as usual and show you how to solve a couple of these exercises. But again, if you're watching this video on your own, you may want to pause at this point, try the exercises for yourself, and then I will show you in a moment how to solve some of them. So this time around, I'm going to leave you to try exercise 1 on your own, and I'm going to have a go at exercises 2 and 3. And exercise 2 was to do with perfect numbers. So what we're going to do first of all is we're going to define a little helper function called perfect, which decides if a number is perfect for us. So it returns true or false. And remember, a number is perfect if when you compute all of its factors and you exclude the number itself and then you sum up what's left, then you get the original number. So for example, 6 was perfect because we take its factors 1, 2, 3, and 6. We throw away the 6, sum everything else, and we get back to 6. Okay? So we can basically just implement this idea directly in Haskell. So we say a number n is perfect. Let me write down the definition, and then I'll explain how it is working, which is very simple. And then we have equals n. So the component parts here is if I want to decide if a number n is perfect, I first of all compute its factors. So for 6, that would be 1, 2, 3, and 6. I don't want the 6, so I throw the last thing in the list away. And that's what init does, throws the last thing in the list away. And then I sum what's left, and then I check, is that equal to n? So that's basically just implementing the idea of what a perfect number is directly. You may have come up with some other possible definitions, so let me give you another possible definition. There are many more too. Here's an alternative way of defining sum. I could say if I take the sum of all the factors of n, and then I subtract n to exclude that one, then that equals n. So that'd be another possible way of defining it. If I asked you a question like this in an exam, unless I said, oh, you need to do it a particular way, any kind of definition would be fine as long as it worked. But for me, I like this one because it basically implements the idea very directly. And then just to complete the exercise, we can define the perfects function. So what perfects is going to do is you give it a number and it's going to return all the perfect numbers up to that limit. So this is just a simple list comprehension. We form the list of all values x such that x comes from the list 1 up to n. It's a simple generator, and then we want to only keep the numbers x if they are perfect. Okay, so a simple one-line definition. A number, we're going to calculate all the perfect numbers up to n by ranging x from 1 up to n, and then only keeping the ones which actually satisfy the property of being perfect. So again, a nice simple one-line definition. So now let's have a look at the last exercise, exercise 3, which was to calculate the scalar product of two lists of numbers, which is expressed in mathematics like you see here. So we can implement this idea very directly in Haskell. So let me define a function called sp for scalar product, and it's going to take two lists of integers, one at a time. We'll make it a curried function, and it's going to give back the integer result. And what we can try first of all is we can basically just implement this formula here directly in Haskell using indexing. So we could say the scalar product of two lists x's and y's is going to be the sum, and then inside we're just going to index into the two lists. So we take x's, index in at position I, times y's, index in at position I. And then where do we get the indices from? Well, the indices we can draw from the list 0 up to n minus 1. Okay, so the only thing we need to think now is what is n? Well, n, we could have a little where here just so it fits on the line, where n equals the length of x's. And we're assuming here that the two lists have the same length. So what we've done here basically is implemented all the components of the mathematical definition in Haskell. Here we have I ranging from 0 up to n minus 1, so that's that part here. Here we're indexing into the two lists, which is that part here, and then we're summing, which is the sigma over here. So we've implemented all of these ideas directly. But it turns out there's actually a cleaner and simpler definition in Haskell. So what we're going to do is take this away. Let's get rid of that. And let me show you a cleaner, simpler definition for this. So all I'm going to do this time around is I'm going to sum the list of all the multiples xy such that xy comes from the result of zipping the two lists together. Okay, so for me this is a simpler definition because all I'm going to do is zip the two lists together, so that will pair up the corresponding components. So we'll get the first thing from the first list and the first thing from the second list and so on. Then we take each of those components, x comma y, one at a time, multiply them up, and then we sum the result. So for me, this is a cleaner and also simpler definition of scalar product in Haskell. So that's it for today. I will see you again, as usual, next time.